V motor of T would look something like this. Be periodic with a period T. And we would say that it was high for a fraction of the period D. All right. So in other words, D is a fraction between 0 and 1. Okay. And so as I've drawn it here, I don't know, D is about 0.25. In other words, this guy's high for about 0.25. Is that a DC waveform? It's AC waveform. It's pulses, right? So that is an AC waveform. It repeats, right? It's periodic. It's a Fourier series. Okay. So it's got a Fourier series, which means, does it have a DC component? Yeah. So the voltage that I'm applying to this motor has a DC term plus a whole bunch of other sine waves, other frequencies. All right. Now, that means that this motor is filtering. All right, is what it's doing. So, in fact, that's happening all over the place. The lights that you see right up there are turning on and turning off, and you're not seeing that. Why is that? Because it's happening so fast that your eye can't see it. It's like the series of images on the TV, right? It's just a series of still images that are passing by. That's another effect of, like, if I have two cameras that are different, that's when I start seeing some oddities, right? But yeah, there's a series of still images that if I throw them together, it looks like a smooth image. Your eye is low pass filtering as it passes the information to your brain of what it's seeing. It can't see the changes happening that fastly, so it just sees these kind of smooth variations. So the way of thinking about this, for me, the motor is a low pass filter. So I had, let me see. All right. All right. And I don't want to listen to myself. So, all right. So what I've got is a DC motor, and then what I'm going to show here is the voltage that I'm applying to it. Or not. Maybe. All right. And then this is my drive. All right. So I have all this stuff showing how it's getting driven. All right. So let's eventually here. All right. All right. So what I have is, so notice what's going on here is I've got a series of pulses that are on that oscilloscope. And what I see is the motor spins and stops and spins and stops. Now, let's say I want it to spin continuously, which is what I want it to do. So what should I do to make it spin continuously? Well, I could make this guy constant, right? Make this input constant. That would work. The other thing I could do is I could speed it up. All right, so let's speed it up. This is what let's see. So I changed the frequency here. So I changed the frequency to 1 kilohertz. All right, so then I zoom in on this. There you go. So now you can see that's a 1 kilohertz waveform. And that's just noise. Now this is that behavior of two things kind of happening together. So it's doing something called aliasing, but it's happening continuously now. All right. What's going on is the motor is filtering out all of the AC terms. The motor is only responding to the DC term. All right. Now, why do we do this? Because if I do this, my motor drive is essentially lossless if I do it this way. And let me ask you this. Let's say I wanted to change the DC value. All right, so let's go back to my picture here. All right, not that. I grabbed that from an old slide deck. Let's say I wanted to change let's say I want this thing to go faster. Right? If I wanted to go faster, you said I needed to apply more DC voltage. How could I change the DC voltage here? There's a DC component to this, right? How could I increase the DC component of this? How could I make the DC component of this VM bigger? What could I change about this? Don't want to change the power supply, right? Because if you think about it, I can't change anything about a power supply, right? Once I got a battery, I got a battery. I'm stuck with it. What would make the DC value of this change? That would work. I could do that. You're right. But that would be tricky to do on the fly. How can I make the average value of this go up? Duty cycle. What would I do? So I'd push this pulse out further, right? What's that going to do? That's going to increase the area under the curve. That's going to increase the DC value. So I think what I'm probably about to do in my video here is to make it slow down, I think. Right now I got this at 50% D. So I think what I'm going to do is make it 10. Yeah. And if I look at that, he's going slow. He has a little trouble going uphill, right? That's the effect of gravity here going on here. The fact that the motor's not perfectly aligned in its seating, but I can see that it's moving pretty slow. Now, I think what I'm going to do is take it up to 90%, I think. I'm just talking there, probably. All right, so let's kick it up to 90%. Yeah. And now he's going a lot faster. And if I look at that, you can see that the average value of that waveform is significantly different, right? He's high 90% of the time and low 10% of the time. That's the idea of pulse width, right? Pulse width modulation. I'm changing the width of that thing. Now, this turns out to be a really efficient and easy way to control a motor, right? And that's why we do. I say efficient because I can technically do this with almost 100% efficiency. All right. We don't need to talk about why that is. That's kind of outside the scope of this class, right? But the concept of what I'm dealing with here is an important one. So if I change this D value, I could think of it like that. Now, what that means is that this motor, from a voltage input to a speed output. So the way I talked about speed was a capital Greek omega, right? This guy has a transfer function, omega. And so this is going to cook your noodle later. Omega of omega. All right. So what we're saying is there's a transfer function for that motor itself, where the input basically is the voltage I apply, and the output is the speed at which it turns. All right. And there's got to be some low pass behavior to the way that thing behaves. And there is, right? And you worked out what that was previously, but I'm not going to get too into it right now. All right. But the basic idea should make some sense. Yeah, Jason. What would happen if you said well, that would only matter if the circuit was second order and underdamped. In this case, it turns out to be second order, but it's pretty heavily overdamped. So there wouldn't be a resonance that I'd have to worry about. All right. Here's a similar example, right, that we can kind of think about where I have an input voltage. Okay, I should call this guy V in. And I want to look at the voltage across the capacitor V out. Okay. Again, of time, because in the time domain, it's like an oscilloscope, like I just showed there. I'm applying a time domain waveform, right? I can see it in the real world. In this case, I'm saying I'm going to apply this voltage. And in this case, it's 5 volts and then it's 0. 5 volts and then it's 0. And I'm going to apply it to this RC circuit. Okay. This RC circuit here is just like my motor. Right. In the case of my motor, the way I sometimes write this is I think of it as there's a transfer function that relates an input X to an output Y. In the case of my motor, my input was the voltage applied to the motor and the output is the speed of it. In the case of this circuit, V in is my input and V out is my output. Okay. So, all right. So what I want to do is I want to think about this. I want this RC circuit to do the same thing. In other words, I want this RC circuit to have a smooth output, right? So what would that mean? All right. So if this V in of T is my input, and let's say I wanted the output to be constant, right? That's what I'm saying is I want V out to be constant. Given the way I drew this, what's the target value? What would be so what's the DC value of this? No, not the DC value. 2.5. 2.5, right? Because the average value would be 2.5. So I want it to be 2.5 volts. Okay. Now let's think about this. I want to be able to draw its Fourier transform. So we've done this before. All right. Basically, we said that Vn of omega is basically this series alpha n delta omega minus n omega naught, like that. All right. So the way that worked out is it says, okay, there's a pulse here, and then there's going to be a pulse at the fundamental. All right. And we worked out what these values are. The alpha n for this case is 5 over j times 2 pi n times 1 minus e to the negative j pi n. Right, for n not equal to 0. Right. If n was equal to 0, alpha 0 worked out to be 2.5. Right. If I go through this, I don't know the exact values, but what I do know is I'm going to see something like this. There's only going to be odd harmonics. And as the frequency gets higher, these guys get smaller. Okay. Okay. So again, what the heck does that? Okay, so we need to understand what the top picture there, Vn of t, that's what the voltage actually looks like. Measure with oscilloscope, that's what I see. What is it? And this is something you really do need to understand for the exam, right? What is Vn, absolute value of Vn of omega? So I'm drawing the magnitude of that thing. What the heck is that telling me? If I see two impulses here, right? One at omega naught and one at minus omega naught, what does that mean? What does that relate to? Those are alpha n values, yeah. So which means that in the time domain, how does this impulse at omega naught and negative omega naught relate to something in the time domain?
The cosine.
Yeah, there's a cosine. So in other words, that these tell me the amplitude of the cosine of omega naught. And this tells me that the amplitude of the cosine at 3 omega naught is smaller. And the one at 5 omega naught is smaller than that. Right? So it's that type of thing that it's telling me. All right. Now, according to what I'm saying here, what is my target for V out of omega? Because this is the way we design, right? We often design things using this math that we've been learning to say, my desire for V out of omega is to do what? Be constant. So what is it in the omega domain? 2.5 where? In the omega domain. So V out of omega. V out of t is a constant, right? For all time, it's the same value.
Yeah, so
2.5 located where? Omega equal to 0. All right. So that tells me what I want the h of omega to look like. Now, what I should do, I basically said to figure out the h of omega, the transfer function, I'm supposed to write the differential equation and all that sort of stuff. But you guys know how to get that h of omega just from circuit analysis, right? What would be the transfer function from V in of omega to V out of omega for this circuit? If I do voltage division, then I should get that h of omega is equal to 1 over j omega RC plus 1. Where I'm going to say tau equals RC for now. So I'm going to say J omega RC plus 1. Now that's a complex function of a real variable. Omega is an input. It's a real number, right? It's a complex output. Okay. All right. So what we're saying is what I want is I want V out of omega. If I plotted that in the frequency domain, my target would be for that to just simply be an impulse at of area 2.5 at omega equal to 0. Right? So if Vn of omega if V in of omega is at 2.5, and then it's got some other impulses that are getting progressively smaller as frequency increases. How do I know they're getting progressively smaller, by the way? Because I know that there's this dependence on 1 over n. So as n gets to be bigger, right, it's going to get smaller. All right, so what's the relationship between V in and V out? How does the transfer function relate those two things? Well, okay, but just more generally, right? How does V out of omega relate to V in of omega? Yep. And if I do it specifically for the magnitude, it's like that. They multiply each other, right? So looking at this picture, what should the transfer function be doing here? Clearing out the other impulses. In other words, basically my target for h of omega, I guess, if you would be to say that my h of omega should look like this. Right? It should basically be a box, right? Where it extends from some low frequency on the positive side to some low frequency on the negative side, and basically is 0 everywhere else. That would be my ideal. Does that happen for this particular thing? How would I know? How can I see if it does? This is what I determined here. All right, how can I see if it does? Well, one way to do it would be to do what I did here, and I went into MATLAB. All right, and I specifically did this here. I let tau be 0.5. Okay, 0.5 seconds would be the units on that. And then I made an omega vector that goes from 0 to 100 hertz. You're not going to like what I did here. 0 to 100 hertz. I multiplied it by 2 pi. So this became an omega value. This is going from 0 to 628 radians per second, I guess. All right. And then I plugged it into the h function. And let's plot that. Let's plot the absolute value of it. All right. So if I plot that, I get this. That doesn't look quite like what I drew as my ideal. My ideal, right, was this box, right, that was equal to 1 and then drop down to 0. That is not what the real world gives me. All right, the real world gives me this. And when I look at this, how would I, so is this ever going to give me, if I keep going, is this guy ever going to get to 0? You guys should be able to figure that out, right? If I look at my, where is it? Here's my h of omega. If I asked you to tell me what is the magnitude of that, right? You should be able to give me an expression without going to MATLAB. 1 over j omega tau plus 1. How can I get a function for the magnitude of h of omega? Yep. So it's 1 over the magnitude of j omega tau plus 1. So that becomes 1 over square root of what? Omega squared tau squared plus 1 squared. Do I square the j? No. All right, I squared the imaginary part of it. All right. So this, if I look at this, how can I tell that this is never going to be equal to 0? For any value of omega, how can I tell that this is never going to be equal to 0? If I was a good math instructor here, I would say I would take the limit as omega does what? As limit as omega approaches infinity, what does this guy become? 0. So in other words, the limit, all right, is 0 as omega approaches infinity. But I'd have to get all the way out to infinity for this thing to ever reach 0. So in other words, this guy's not doing what I want it to do. But it's kind of, if I look at the picture of it, right, it is kind of approximating it, right? It starts out at 1 and kind of drops off, but it's a smooth drop off. It's not a sharp drop off, okay? So, and it's never actually going to hit 0. So my goal would be for V out to be a constant, but that's not possible. So what could I do as an alternative? All right, so V out can't be constant. So what can I do as an alternative? What I want to have happen is that the first harmonic, let's call it V out 1, which would, have some shape C1 cosine omega naught t plus, I'll call it phi 1, right? And I can relate that to the alpha type of the series by saying it's 2 times the magnitude of alpha 1 cosine of omega naught t plus the angle of alpha 1. Right. What am I saying that how could I this is what it is. What I'm saying is, what do I want to C1 and the magnitude of alpha 1 to be? What do I want them to be ideally? Right? If I'm only having the result be a constant, what is it that I want C1 to be? Well, this is the fundamental term. This is a cosine term, right? So what do I want this to be? Do I want this fundamental term? Do I want it to appear in my output? I said I wanted the output to be constant. Constant means flat, right? So what do I want C1 to be? If that was a constant that was not 0, then I would have a fundamental term. So what does C1 have to be? What does C1 have to be? 0. C1 has to be 0, right? So in other words, this thing doesn't appear there. This is my target, though. What I am saying is that's not possible. Okay, that's not actually possible. That would be my target. So what I do is I basically have to say, all right, as an alternative, what I want to do is I want to make sure that this C1 is approximately 0. This gets into the fun engineering stuff, right? What's approximately 0 mean? Very, very small, right? So if the output here, if the output is supposed to be 2.5 volts, right? I want it to be constant, and I really want it to be 2.5 volts. So what could I do? What could I say about C1? What would be a good target instead? I can't target to make it 0. What could I target to make it? Something small. Yeah. Well, so how about what if and I could probably choose anything. Let's say I said, I don't know, let's say I wanted it to be 1% of 2.5. Right? 1% of 2.5. So that means that if I were to look at V out of t on an oscilloscope, it would be like this, constant, with a little bit of ripple on it. In other words, it would be going, if C1 was 1% of 2.5, or what is that? That's 0.025. That it would be going 25 millivolts above 2.5 and 25 millivolts below that. Right? How would I make that happen? What would I have to do to make that happen? Well, you're thinking good thoughts in terms of what I would have to do physically, but just to get the math equation out, because the math equation tells me how to change the capacitor. There's 2 ways to change the capacitor. One is to go to the drawer, pick one out, see if it does it. And if it doesn't, go back to the drawer and put another one in. And then Benny's happy because he got this big pile of capacitors. Right? That's Benny's least favorite thing in the planet. Right. So, but there's a math way to do this, right? Well, but what I can say is h of omega's magnitude is 1 over square root of omega squared tau squared plus 1, right? And I know that the magnitude of V out of omega is equal to the magnitude of h of omega times the magnitude of v in of omega. And what I just said is I want the magnitude. Now, because what I'm looking at is these alpha values, right? I'm not looking at the C values. It's saying that my target for C1 was for it to be 0.025, or for the alpha value to be, so the alpha 2 times, what would that be? 0.0125, right? This is my magnitude of alpha 1, right? That is the value of the Fourier transform at omega naught, right? The value of the Fourier transform at omega naught should be less than 0.0125. All right, so what I'm saying is at omega naught, specifically at that frequency, whatever frequency that is, I want that to be 0.0125, and h of omega naught times Vn of omega naught. So what I can do is, for my input, I know what this is, right? Right? I can calculate that. So what's that do? It gives me a number for what this is going to be, because I can plug in omega naught here, and I can say, all right, how do I choose a value? In this case, it's either how do I choose a tau value, or how do I choose an omega naught value so that this becomes true? Okay. Well, one way to do this, so in this case, if I'm talking about the RC circuit, I can change the tau all day long. I can go to the drawer and get different R's and get different C's, and I can make this work. In the case of the motor, it's not quite like that, because I can't just go and get a new motor, right? The motor, it's the time constant of the motor is inherent to the motor, right? So I can't do that. So what I can do is I can change what omega naught is, right? That's what I did in that video. I started out with omega naught being a low value, and I put a square wave in, and I got a square wave out, right? Because I was doing it at a very low frequency. Once I did it at a high enough frequency, the only thing I got out was the constant. All right. So what I've got here is a constraint that I can design with. All right. So if I knew what the magnitude, let's just say, for sake of argument, that 0.0125 equals h of omega naught. And let's say that the magnitude of this, and I think it works out to be about 1.59 for that square wave. All right. What's that tell me? This tells me that the value of h omega naught needs to be what? 0.0125 divided by 1.59. Right? So if I do that math, all right, 0.0125 divided by 1.59, the magnitude needs to be 0.0079. So what would I do with that? Well, what I would do with that is I would go to the graph here, right? And what would I do? I'd find where the magnitude is equal to 0.0079. That is the frequency that the omega naught should be at, right? If I place it there, then that ripple, that variation, that sine wave that I have at the fundamental frequency and the speed will be tiny, right? It'll be 1% of the average, right? That's how we apply this. Now, this is a tricky looking graph to look at. Why? Because there's a crap load going on in a very small frequency range. In other words, this guy starts at 1 and he's pretty quickly gone down to 0.1, right? That's a goofy looking graph if I'm going to use it for anything. So what do I do as an alternative? Well, you've probably done this already with Yahoo. I put it on a log scale, right? What did I do with my log scale? There it is. I put it on a log scale. What the log scale does is it basically expands the axis. So it expands out what's happening at the low frequencies, right? It just basically is a way of zooming into the graph to show me more of that area where I've got a bunch of action happening. All right, that's the basic plan. Now we're gonna look at that more on Friday, right? I wanted to get the basic concept out today. All right, and this you got a couple of problems like this that you're gonna deal with in the homework or in the project. Sorry.
we have 5 problems.
I don't know how many you're gonna have. No more than that.
That's okay.
No more than 5. Yeah.